السلام عليكم ورحمة الله وبركاته. See where we stopped yesterday. Let me share the screen first. Okay. Oh, pipe head loss. This is where we stopped today. We're explaining the pipe head loss. All right, let me take it to the presentation mode. So we were explaining the pipe about pipe head loss, and we say we use the Dasio-Weisbach equation, and the pipe head loss is made of two types: total head loss, which consists of pipe head loss or the major head loss, and the component head loss or minor head loss, which are the losses, due to the presence of valves, bends, teeth. All these losses in the component head loss usually occur due to creation of oscillatory zone, or separation zone. You remember we explained the separation zone and the work region. And we said in the work region, you have head loss, okay? Because of the flow separation, okay, huge amount of energy is lost in that process, okay? So we are going to expatiate more with the aid of some diagrams, okay? The pipe head loss, we call it major head loss, and the component head loss, we call it minor head loss, okay? So the derivation of the Dasio-Weisbach equation, we may not go into the details, but it's very pretty simple and straightforward. Due to time factor, we will explain the basic principle. It is simply balancing of forces, application of the momentum equation, or Newton's second law of motion. You have a fluid element, you have a container, okay? This is the direction of flow, okay? So we're considering a cylindrical volume, and we analyze the forces acting and applying the Newton's second law of motion, okay? The forces acting, you have the pressure force, you have the shear force acting at the walls, at the boundaries, okay? And you have the gravitational force. Because it is tilted, then it will have component in the direction of flow, okay? So you have basically three forces: pressure forces, which is P1A minus P2A, minus the shear force, which is tau naught, shear stress times the area. The area is pi d times dl, which is the length. And then you have the weight component, okay, which is simply W sine theta, sine alpha, okay, and sine alpha is simply equal to delta Z over delta L, okay. So upon simplification, we'll arrive at the head loss to be equal to FL, or let's simply take it here gently. You have the pressure force, shear force, and the weight, gravitational force, okay. This is the net pressure force, which is P minus P2 times the area, minus the shear force, which is in the opposite direction because it's frictional force, basically, okay? And then you have the weight force, which is also, whose component is opposite to the direction of flow, which is gamma. This is the volume, okay? Gamma times volume gives the weight, then times sine alpha. And sine alpha is delta Z over delta L, okay? So if we simplify, we substitute sine alpha as delta Z over delta L, and try to simplify the equation. You divide by d pi, you will have it this way. Okay, pressure, piezometric pressure, the difference in the piezometric pressures. Okay, and again, if we recognize that, when we apply the energy equation to the control volume, we don't have a pump or a turbine. V1 equals V2. Okay, the velocity is the same because we're talking about uniform and steady flow here. And alpha 1 equals alpha 2. So when we apply the energy equation, we have it this way. Okay, so HL will now be the difference. Okay, this is from the energy equation. So we just replace this with gamma HL here. Okay, and then make HL the subject of the formula, which is the head loss, because the difference in the piezometric pressure as water is flowing through a pipe, piezometric pressure is declining. Okay, 0.1, 0.2. The difference is because of the head loss. Okay, the head loss is what is responsible for the difference in the piezometric pressure. Okay, between 0.1 and 0.2. Okay, so this is the piezometric pressure. Piezometric pressure. The difference between the piezometric pressure is responsible for the piezometric head loss. Okay, it's due to the piezometric head loss, which is given as gamma HL. Okay, and gamma HL simply rho GH. Okay, because this is also like a head of water that is being lost, so it is expressed in form of a head of water. That's why we call it head loss. So the head is being lost as it is moving, it's decreasing. Okay, so it is being lost. Okay, and then once we substitute, we make it the subject of the formula. Okay, and introduce new symbol HL because this is the major head loss, which is the frictional head loss. Okay, or head loss due to friction. We have HF equal 4L tau naught D gamma. Okay, so head loss in pipe. Now we just introduced the kinetic pressure here. Okay, and then rearrange it. Okay, we now rearrange it. We remove this out, which is now constant. Okay, L. So this is our F, which we call friction factor or resistance coefficient. It has many names, but normally we call it friction factor, or sometimes it can be referred to as resistance coefficient. Okay, resistance coefficient. It is a pi group, meaning it is a non-dimensionless number. Okay, pi group, the non-dimensional, the dimensionless groups. Okay, that's ratios like Reynolds number, like Froude number. Okay, we will explain about Froude number in chapter 15. Okay, so we have placed this constant because this is a constant. The shear stress. Okay, once it is fully developed, the shear stress becomes constant. We explained this yesterday. Okay, and the velocity is constant. Okay, and then the density is constant. So the friction factor is simply like approximately equal to the shear stress acting on the wall over the kinetic pressure. Okay, over the kinetic pressure. So this is called as Weisbach friction factor, and the resistance or resistance coefficient. Okay, so like I said, it has different level, different names. Friction factor, that's the friction factor, that's Weisbach friction factor, and resistance coefficient. Okay, and there's also another coefficient called fanning coefficient, which is usually used by chemical engineers. Okay, and the Darcy friction factor is 4 times the fanning coefficient. Okay, so this is the Darcy-Weisbach head loss equation, which is one of the most important equation in fluid mechanics. Okay, HF, that is the frictional head loss, is given by F L over D V squared over 2G. Okay, and to use the Darcy-Weisbach equation, the flow should be fully developed. And why do we say it should be fully developed? Because that is when the velocity will remain constant. Okay, that is when the average velocity doesn't change, it remains constant over time. Okay, And then again, the shear stress, also the wall shear stress remain constant. Okay, when it is fully developed. At the beginning, at the entrance, like I explained yesterday, the shear stress is maximum at the entrance, and then it will be decreasing because of the reduction in the slope of the velocity profile. Okay, until it becomes fully developed. Okay, that is when you have the minimum shear stress, and that minimum shear stress is maintained. You remember this curve? Okay. Okay, which remains constant when it is fully developed. Okay, the shear stress. Okay, this is with distance x s. That is the streamwise in the streamwise direction. All right, we'll look at the application of the Westbach equation. Okay, in some examples to come. Now we'll briefly look at stress distribution in pipe flow. We explain about the shear stress, okay, the shear force, okay, the shear stress. And if you remember, when discussing viscosity, we briefly talked about the stress distribution as well. But here we will make some derivation and support some of the conceptual knowledge that we explained under the shear stress and viscosity, okay, previously. So this is a pipe in which water is flowing, and the pressure distribution is hydrostatic, okay, across any plane normal to streamlines. This we explain using the Euler's equation, okay. The pressure distribution is hydrostatic along any plane parallel to the streamline. Along the streamline, the pressure distribution is given by the Euler's equation. The Euler's equation is delta P z, okay, minus delta P z equal rho A, okay, and the acceleration. Okay, so if the fluid is accelerating in this direction, it means the pressure distribution, the pressure gradient is increasing in the opposite direction. Okay, if it's accelerating in this direction, then it means the pressure distribution is increasing in the opposite direction, meaning the pressure is decreasing in the direction of acceleration. Okay, now when it is parallel to the streamline, we said because when it is parallel, the acceleration is zero. Okay, the tangential, the normal acceleration is zero, because when you have streamline that is straight, you don't have acceleration. The component of the acceleration, okay, this is the tangential acceleration. The normal acceleration component is zero in this case, and when it is zero, so you have delta p z equals constant. Okay, if it is equal to constant, then this is the statement of the hydrostatic pressure distribution. Okay, dp dz equals minus gamma, which is also constant. Okay, so the pressure is hydrostatic. Okay, for any plane normal. Okay, and by hydrostatic it means it increases linearly with depth. Okay, it increases linearly with depth. Okay, so this is the linear, increment, it increases down. You can see due to the weight of the fluid acting. Now, to analyze the stress distribution, okay, in this case, we still use the force diagram. We have the pressure force, the shear stress, and the weight, okay? But here, instead of using P1, P2, we use an incremental pressure, okay, in the direction of flow, okay? P plus dP ds times delta L, okay? And then we apply the Newton's second law of motion, which gives us zero because the velocity is constant. So the acceleration is zero, because if the velocity is uniform, then that means acceleration is zero, because acceleration is the change in velocity. Okay, when you don't have a change in velocity or change in direction, then the acceleration is zero. Okay, but if you have any of this, then the acceleration will not be zero. Okay, so here we are assuming that the velocity is uniform, hence the acceleration is zero. Okay, so when we substitute, the pressure force, this minus that, which is always compressive, minus the shear stress, which is the shear stress times the area. Okay, and the area will be 2 pi r times delta L. Okay, 2 pi r to the circumference, then times delta L, okay, which is the surface area. Okay, minus W sine alpha. Similar to what we did in the derivation of the Das-Weisbach equation. Okay, I'll replace sine alpha as delta Z over delta L. Okay, and W, which is gamma A delta L. Okay, once we substitute and simplify, we will arrive at the shear stress to be equal to R over 2. Okay, minus D by ds P into P plus gamma Z. So what is the interpretation of this equation? Okay, the shear stress distribution in pipe flow. If you look at it here, it means when R equals 0, the shear stress is 0, meaning at the center line, because R equals 0 at the center line, isn't it? At the center, okay? So you have 0 shear stress at the center. Hence, you have the velocity to be maximum. That's why you have the velocity to be maximum at the center, because it is unaffected by the shear stress, by the shear force, okay? So when R equals 0, you have the shear stress to be 0 in that case, okay, which corresponds to the center point. Okay, and then, yeah, you can see R starts from the center, okay, so it increases linearly, okay. Equation 15 shows that the shear stress distribution varies linearly with R, okay, that is this equation. It varies linearly with R, okay. As R increases, the shear stress increases, okay. So that's why you can see as R increases, the shear stress increases. It is maximum at the at, at the wall, okay, and minimum in the center line, okay, and there is linear increment, okay. It varies linearly with R, okay. So that's why you can see here it increases this way and that way, okay, because as it moves closer to the wall, it increases, okay, due to the boundary, okay, because the boundary layer increases, okay, towards the wall, where you have the viscous effect to be greatest, okay. So you have linear shear stress distribution here, and you should notice that shear stress is 0 at the center line. It reaches a maximum value tau naught at the of tau naught at the wall, okay, and the variation is linear in between, okay. The variation is linear in between. And this linear shear stress variation applies both to laminar and turbulent. It applies to both laminar and turbulent flows. Okay. Now head loss in laminar flow. Recall that the Weisbach equation is applicable for both laminar and turbulent, and round pipes and also non-round pipes. Okay. In water engineering, in civil engineering, more often than not, we encounter only round pipes. Okay, but in chemical engineering, you can encounter pipes that are not round, like ducts. Maybe rectangular that are used, let's say, for cooling and what have you. Okay, and there you will need to define what is called the hydraulic diameter, DH. Okay, hydraulic diameter, which is simply 4 times the surface area over the weighted perimeter. Okay, this is surface area over the weighted perimeter. So this is how to find the equivalent value for, let's say, when we're using the Reynolds number VD over mole. Okay, so this is, if it is non-circular, you use this. You find the area of the shape over the weighted perimeter. The weighted perimeter is the perimeter of that is in contact. Let's say here it will be this is A, let's say B. So it will be 2 into A plus B. That is B plus A plus B plus A. Simple. That is the weighted perimeter. But like I said, in civil engineering applications, more often than not, we encounter circular pipes. Okay. So, but just so you know, this is called hydraulic diameter, and it is 4 times what we call the hydraulic radius. Hydraulic radius is simply area over the weighted perimeter. Okay. Now, laminar flow in a round tube. This section describes laminar flow and derives relevant equations. Okay, so here we'll look at the relevant guiding equations for laminar flow as well as turbulent flows. Okay, and then do some computations here and there to demonstrate the application of the relevant equations. And the laminar flow is important for flow in small conduits, okay, called microchannels, for lubrication flow and for analyzing other flows in which viscous forces are dominant. Remember, laminar flow is sometimes synonymous with viscous, flow, because viscous forces are dominant in laminar flow. Okay, but for turbulent flow, viscous forces are not dominant. Okay, because you have high velocity. Viscous forces prevent, high velocity of flow. And also, knowledge of laminar flow provides a foundation for the study of advanced topics. Okay, like as we mentioned earlier, normally flow in pipes, most usually water flow in pipes is more often than not turbulent, but it gives, the foundation for the study of advanced topics, because sometimes the flow can be approximated to be laminar, and sometimes the same equation may be applicable for both laminar and turbulent with some slight within some accuracy level. And laminar flow is a flow regime in which the fluid motion is smooth, okay, and the flow occurs in layers. This we explained before. And the mixing between layers occurs only by molecular diffusion, okay, only by diffusion, maybe if there's difference in concentration, okay, and a process that is much slower than turbulent mixing. Turbulent mixing because of high velocity, so there is mix up, of the layers. And according to the equation 10.2, laminar flow occurs at Reynolds number less or equal to 2000, okay, and turbulent flow occurs at Reynolds number greater than 3000. But don't forget, like I mentioned in other text, it occurs, they say it occurs at 2300, and turbulent flow at Reynolds number greater than 4000. Okay. Laminar flow in a round tube is called Poiseuille flow, or Hagen-Poiseuille, in honor of researchers who studied low-speed flows in the 1940s. Okay, so laminar flow is called Poiseuille. Okay, it's the name of, I think, French scientists. This is another one, Hagen and Poiseuille. Okay, so we call it Hagen-Poiseuille flow. Now, what is the velocity profile in laminar flow? We'll simply, explain this derivation, because what we are interested in generally here is something that we know before, that velocity profile in laminar flow, the average velocity is equal to the maximum velocity over 2. When you have laminar flow in a pipe, when you consider a section and try to draw the velocity profile, okay, this is the maximum velocity here, Vmax. Okay, but more often than not, we don't represent the velocity as, we don't use the velocity distribution to simplify our computational work. Okay, so we normally use an average velocity of flow. Okay, an average velocity of flow, in which for laminar flow we will derive and prove that the average velocity of flow, which is V bar, is equal to the maximum velocity of flow in the pipe divided by 2. So the maximum velocity is twice the average velocity. So this is the relationship. This we mentioned before, if you can remember. Okay, and this is for laminar flow. For turbulent flow, the average velocity is about 0.8 to 0.9 of the maximum. Okay, we mentioned before. Okay, but 0.8 to 0.9, because for turbulent flow, the velocity distribution is more or less uniform. It's more or less like a plug. Okay, it's more or less like a plug. Okay, so the difference between the average velocity and the maximum velocity is not very much. Okay, you can see just 10 to 20% for turbulent flow. But for laminar flow, because of the effect of viscosity, okay, the effect of viscosity, so you have the flow to move in clearly defined layers and with very low possibility of mixing, okay, between the adjacent layers. Okay, so like I said, this is the summary of what we want to here, okay, in this derivation. But let me just take you over briefly. Here we start from the Newton's law of viscosity, okay, that the shear stress, is proportional to the velocity gradient, dv dy. And then we try to split this using the chair rule in calculus. Okay, dv dy, we make it dv dr. We just introduce r, we introduce dr here. We haven't done anything. And then we look at what we change y. We let y to be r naught minus r, where r naught is the pipe diameter and r is the radial distance. Okay. R naught is the pipe radius, that's the total radius, and the radial distance is r. Okay. And then when we differentiate the r dy from here, we have -1. So that's why we have the minus sign here. Okay. And then substitute equation 10.6 into 1015. Okay. 1015 is the shear stress formula which we derived before this one. Yes, this is the shear stress distribution in pipe flow. Okay, so we now substituted for the shear stress equation. Okay, so it is substituted, and then simplified. Here you have the RDS, different variables, and they are equal. So they can only be equal if they are equal to a constant. Okay, if they are equal to a constant. Okay, because you have different variables. Okay, dr and the other one ds. Okay, so the equation can only be equal if they are equal to a constant. So we took one side and equated to a constant. Okay, what is this? Then try to make it into delta. Okay, we change it. This is the piezometric pressure, okay, which is given by gamma delta H, which is the piezometric head. Okay, H is the piezometric head. And then from here, we now equate this to this. Okay, which is dVdr. Okay, so it's now equal to this. And then here, remember delta H, we now integrate. Okay, we now take the R here and integrate. Okay, and integrate. And when we integrate, we will have a constant of integration. Okay, which we can apply the no slip condition to find the boundary condition, because the velocity is 0 at the wall, isn't it? So at r equal r naught, the velocity is 0. So when we substitute, we can find c, the constant of integration, and then we substitute it back into the equation here. Okay, and then when we solve for c, we substitute it into 1020 here. So now this is our new equation. Okay, this is the velocity. And the maximum velocity occurs at the center line, which is r equals 0, isn't it? At the center line of the pipe. Okay, at the center line. Okay, that is r equals 0. So V max, we substitute r equals 0, and we have it like this. Okay, and then combining equation 22 and 21. 21 and 10.21 and 10.20, that is by taking the so here, if you look at it very well, this is V and this is V max. Okay, and what is common in this case is this. Okay, so we can go back. This is VR. We can remove this and substitute V max this point here. Okay, So we have VR equal Vmax into 1 minus R over R naught squared. This is simple substitution, okay? And then when we take the ratio Vmax, V, the average velocity over Vmax, that is when you have the maximum velocity, okay? You have the maximum velocity at R equals 0, okay? When R equals 0, so this is V, okay? You realize that the average velocity is equal to V max over 2, okay? But like I told you, the main point we want to drive home with this derivation is the fact that the average velocity in laminar flow is equal to the maximum velocity over 2. Simple. This is the basic thing that we want to explain here, okay? And the equation shows that velocity varies as radius squared, okay? It varies as radius squared. You can see that, okay? Meaning that the velocity distribution in laminar is parabolic, okay? Okay, it's parabolic. So that's why we draw it like a parabola, okay? We draw the parabolic shape. Like I told you, we have been drawing this parabolic shape, but this gives us the mathematical background, the mathematical proof, okay, on why we draw the parabolic shape. This is VR, which is the general velocity at any distance r, okay? And this is r naught, the pipe radius, and this is the maximum velocity at the center line, okay? At the center line. And the maximum velocity, of course, at r equals 0, I mean at the center line, okay? Is very important. Now, from the same formula, we can now find the discharge, okay? And we can now find the discharge, okay? Because discharge in integral of VdA. Remember the velocity, which is given by this function, and the area for pi, 2 pi r, 10 times dr. So we integrate from 0 to r naught. R naught is the pipe radius. So when we integrate, a simple integration, you know, with respect to r, okay, this is r, okay, so this is basic integration, no complexity. All other terms are constant, okay? So when you apply the integration limits, you arrive at this, and then to derive an equation for the mean velocity, okay, for the mean velocity here, we now divide this by the area, okay, the area of the pipe, which is pi r squared, okay? So that's why here is power of 4 and here is power of 2, okay? Because we divide by pi r squared, pi r naught squared, okay, which is the area of pipe to get the average velocity, okay? Once we get the average velocity, now we can now divide, okay, v over the average velocity, okay? Comparing equations 10.26 and 10.22, which we did before, okay? When you this is 10.22, this one, yes. So when you compare them, when you compare this with this one, you will see that the average velocity is equal to v max over 2, okay? So I explained the basic principle, I mean the point that we want to drive home, that the average velocity in laminar flow is half the maximum velocity, okay? That is the main point here. Now, head loss and friction factor, okay? We explained that head loss, you know, to derive the equation for head loss in a round tube. Okay, we assume fully developed flow. Okay, and we apply the energy equation. We don't have pipe or pump. Okay, so we only, and the velocity head will cancel because it's the same velocity. Okay, the velocity is constant. Okay, so we have the head loss now, which we replace with the frictional head loss, HF. Okay, and we can expand equation 1027. Okay, here we have delta L, delta H. Okay, which is the difference in the head. Okay, which is this. Okay, if you remember the piezometric head or the pressure head. Okay, or piezometric head is given by P over gamma plus Z. Okay, so now delta H is going to be P2 PZ2 minus, because this is PZ piezometric head at 0.2 and this piezometric head at 0.1. Okay, so it's simply the difference between the piezometric heads. Okay, which is delta H. And then when we replace here and delta L with L and reorganize, we will have it to be this. Okay, and we take the difference. Okay, P1, the piezometric head at 0.1 minus the piezometric head at 0.2, that gives us the pressure head. Okay, piezometric head at 0.1 minus piezometric head at 0.2, so it gives us the head loss of gamma HF. Okay, gamma HF. Okay, so that's why here we PZ1 minus PZ2 is now HF into the remaining terms. Okay, using the average velocity here. Using the average velocity. So here we introduce, for laminar flow, key assumptions here. You have a laminar flow, fully developed flow and steady flow, and the fluid is Newtonian. And this equation shows that head loss in laminar flow varies linearly with velocity. Okay, the head loss varies linearly with velocity. Okay, and here also we can use the friction factor, which in this case, the friction factor will simply be 32 mu. No, this is for Darcy-Weisbach equation, which we derived before. Okay, and this is for laminar flow. Okay, so we are equating the two because you remember the Darcy-Weisbach equation. This one is for both laminar and turbulent, L and T. Okay, for both laminar and turbulent, and this one is simply for laminar flow. Okay, in which the head loss is varying linearly with the velocity. Okay, so when we equate this with the Darcy-Weisbach head loss formula, which is F L over D V squared over 2G, we make F the subject of the formula. We find that F is equal to 64 over the Reynolds number. So what we are saying in summary here is this. The frictional head loss in laminar flow varies linearly with the velocity, and this is the formula that you can use to find the frictional head loss. You can also use the previous one, the Darcy-Weisbach equation, to find the frictional head loss if you know the friction factor. Okay, and the friction factor in laminar flow is simply equal to 64 over the Reynolds number. So this is the summary. Okay, and the pressure head loss here in a pipe, okay, the pressure loss is simply equal to the head loss. Okay, it's simply equal to delta P over rho G. Okay, because from here the piezometric head is equal to P over gamma plus Z. So as water is flowing, the piezometric head at these 2 points is dropping. Okay, is reducing due to the head loss. Okay, so at point 1 minus the piezometric head at point 2 will give you the head loss. Okay, the difference in the piezometric head for the 2 points is the frictional head loss. Okay, so that's why the head loss can be defined in terms of pressure drop, which is delta P over rho G. Okay, can be defined in form of the pressure loss. We will take an example, like I said, to demonstrate the application of all this. Okay, but now you need to understand the theoretical background, the formulation. And like I said, here for laminar flow, the head loss varies linearly with velocity. Okay, the head loss varies linearly with velocity. Now, so this is it. Yeah, like I said, this is frictional head loss in laminar flow, and the friction factor is 64 over Ra. Okay, now let's take some example to demonstrate the application of the head loss formula in laminar flow. Here you have an oil whose specific gravity is 0.85 with kinematic viscosity of 6 times 10 to the power minus 4 meters square per second, flowing in a 15 centimeter diameter pipe at flow rate of 0.02 meter cube per second. What is the head loss for a 100 meter length of the pipe? So we are looking for the head loss. Simple, okay? And so the first thing, we should try to find the velocity. We are given the flow rate and the size of the pipe, so we can find the velocity of flow, which is Q over A, okay? And with the velocity, we can find the Reynolds number to know whether it's laminar or turbulent, okay? So we find the Reynolds number, Vd over mole, okay, from the velocity. So 283, meaning because it is less than 2000, so the flow is laminar. Hence, we can apply the head loss formula for laminar flow, okay? So simply everything here is known. The velocity, we already found it, so we substitute. So this is the head loss, meaning the head loss, it lost a head of 9.8, okay, as the oil is flowing in the pipe, okay. The head loss, let's say this is the pipe, okay. So this is the piezometric height here. As it is flowing, there is head loss of at point 2 of about 9.8 meters, 9.83 meters, okay? That is what it means, okay? Frictional head loss here. And this is using the formula which we derive for the laminar flow, head loss for laminar flow. We can also use the Darcy-Weisbach equation because we said it's applicable for both laminar and turbulent flow. So in that case, for using the Darcy-Weisbach equation, we need to find the friction factor, F, which for laminar flow, the friction factor is simply F over 64. F equals 64 over Re. Okay, so this is the friction factor, 0.226. Okay, and then we substitute in the formula for the Darcy-Weisbach equation, and you see we arrive at the same answer, exactly the same answer. Okay, so you can use any of the two methods above to find the head loss for laminar flow. Is it clear? Okay. Now we are done with laminar flow. What we did, we expressed the stress distribution in laminar flow, we expressed the head loss formula for laminar flow, and explain how the velocity varies in laminar flow, the profile, the velocity profile. Okay, so now we will look at turbulent flow. Okay, and for turbulent flow, we know that the movement is chaotic. Okay, and the fluid particles, they move with high velocity and there is mixing, and the velocity profile is more uniform or flatter than the corresponding laminar flow velocity profile. So it is more or less uniform. Okay, for laminar flow, it is parabolic. Okay, and we have shown that. For turbulent flow, it is more or less uniform. Okay, it is more or less uniform. Okay, the velocity profile for turbulent flow because of the mixing effect. Okay, so the particles more or less tend to have the same velocity at every section. That is what it means. Okay, and engineers and scientists model turbulent flow by using an empirical approach. What's empirical approach? Empirical approach is different from analytical. You see, for the laminar flow, we derive the stress distribution, we derive the head loss formula and all that using analytical considerations. By analytical consideration here, we look at the force balance, okay, application of Newton's second law of motion, okay, and then try to, simplify the equations and arrive at the relevant equation. But for turbulent flow, it is empirical in the sense that more often than not, you don't have the governing mathematical formulation. You need to go to the lab, perform experiments, vary this, and come up with certain numbers, certain formulation that is based on the results obtained from lab experiments. Okay, that is why we call it empirical. Okay, empirical are results obtained from lab experiments, okay, which may not have analytical background, which may not have like analytical proof, clear analytical proof. So there you'll be dealing with some constants, power of 0 point this 0, some numbers that were obtained using, some lab experiments. Okay, so because turbulent flow is really a complex one to model analytically, so that is why most of the time we use, the empirical approach. And this is because the complex nature of turbulent flow has prevented researchers from establishing a mathematical solution of general utility, okay, general use, okay. So turbulent flow and Moddy chart. Now, how to characterize a flow as turbulent? We said that a flow is greater than 3,000, in some text greater than 4,000. Okay, and in fact, you can sometimes, when you use a very smooth pipe, you can even have laminar flow up to Reynolds number 100,000, up to Reynolds number 100,000. Okay, if you avoid, disturbance in the pipe, if you use a very smooth pipe, okay. But for general applications, laminar is classified where Reynolds number is less than 2,000 or 2,300. Now, for turbulent flow, the velocity around pipes can be determined using the empirical equation, what we call the power formula. It's an empirical equation in which the velocity at any radial distance r over the maximum is given by r naught minus r over r naught to power of m. Okay, this m is obtained empirically, meaning based on some lab experiments and other factors. So for turbulent flow, the movement is chaotic, eddying, and unsteady in direction transverse to the flow direction. Okay, so it is eddying, mixing. You have a lot of mixing, and you have flow. This is the direction of flow. You have flow even transverse to the direction of flow. Okay. So this is the power law where UR is the turbulent velocity at radius R of the pipe. This is the maximum velocity, which is higher than the average velocity by about 20%. Okay, the maximum velocity is higher than by, while for turbulent flow is higher than the average velocity by 50%. By 50%. This we proved. Okay, that the average velocity is the maximum over 2. And r naught is the radius of the pipe, and r is the radial distance. Okay, and m is has an empirical values, okay, which depends on the Reynolds number. We will show a table, depending on the Reynolds number. This is the value of m, 1 over 6, 1 over 6.6, and here in this case, maximum velocity over the average is 1.26, 1.24. So you can see in all this, like this is like 26% greater than the average velocity, 24%, 22, 18%, 16%. So on the average, for turbulent flow, the maximum velocity is greater than the average velocity by just 10, 20%. While for laminar flow, It is greater than the average velocity by 50%. 50%. Okay. So this is the value of m, depending on the value of the Reynolds number. Okay. And this is the power law equation. Okay, which is an empirical equation. It may appear, to be like analytical R naught minus R because M is empirical. Okay. And this is VR, for laminar flow, the velocity around pipes. Okay. This is Vmax, and this is for laminar flow. Okay. And this is for turbulent flow. Okay. Yeah. This is for laminar flow, and this is for turbulent flow. Now let's take a few minutes break. And when we come back, we will make some few explanations about the friction factor F, okay, for turbulent flow. If you remember, for laminar flow, we said the friction factor is simply equal to 64 over the Reynolds number for laminar flow. So what is the friction factor for turbulent flow? What are the different formulations? Okay, this is what we will discuss. Let's take some few minutes break, and when we come back, we'll discuss more on this matter. Okay. Any question? All right. All right, welcome back. Let's move on. You can see I have 13 participants, so meaning 2 are absent. The class. And at the end of the class, we will discuss something important having to do with the assessment plan. Okay, so don't go out. Okay, at the end of the class, we'll discuss about the assessment plan. Okay. So, okay, let me put it the presentation mode. Okay. So for turbulent flow, like I said, the friction factor for laminar flow is simply 64 over the Reynolds number, okay? But for turbulent flow, there are many formulations, okay? In the 1930s, many scientists have worked on this, Prandtl derived an equation for friction factor for turbulent flow in pipes with smooth walls, okay? The equation started from the V equal Q over A, okay? And the uh, flow rate substituted on the area, and then after integration, applying algebra, tweaking the constants, and to better fit experimental data. Okay, so say to better fit experimental data, so that makes it somehow empirical. Okay, it makes it empirical that way. Okay, because like I said, it deals with the experimental data. Okay. Uh, So I have the friction factor 1 over root F equals this. Okay. This is an implicit because you have F here and F here. It's not an explicit equation. Then in 1933, Nikuratse, who is Prandtl's graduate students, measured the pressure drop and flow rates after gluing the inner walls of pipes using uniform size grain sand. Okay, so he glued uniform size grain on the pipe. Okay, and then why did he do that? Because the rough it is, the more the pressure drop, isn't it? Because from frictional force is higher when you have rough surface. Okay, and Nikuratse developed a new parameter which is the sand roughness height. Okay, the sand roughness height KS. S is the sand, okay? The sand roughness height KS, or a non-dimensional or a dimensionless number called relative roughness, which is KS over D, okay? Which is the the roughness height over the pipe diameter, okay? If you look at it, no matter how smooth the inner surface or the inner walls of the pipe appears, when you examine it under a microscope, you realize it has small, some undulations, okay? So this roughness height, in some texts they use epsilon and in some they use ks. Okay, so here in this text we are using ks, while in other texts they use epsilon, okay, which is simply like this, okay, or okay, epsilon, okay, as the roughness height. But in this text we will be using ks, okay, the sand roughness height. And then he came up with this, the log of 100F log RE, okay, for laminar flow, they collapse onto this blue line. For smooth wall tube, onto this blue line. Then for transitionally rough flow, for fully rough flow, this is the region, okay. But in whichever case, by varying the relative roughness, you can see 0.03, this, okay, this, they all collapse on the laminar flow region, okay. Now, the effect of wall roughness. For laminar flow, the friction factor is independent of wall roughness. So it is independent of the relative roughness Ks over D for laminar flow. For turbulent flow, it depends. Do you have smooth? For smooth tube, because it is smooth, so It is independent of wall roughness for smooth tube. Okay. For transitionally rough turbulent flow, it depends on the wall roughness. And for fully rough turbulent flow, it surely depends on the wall roughness. So here is divided into four. For laminar flow, it is independent of the wall roughness. Okay, for laminar flow. Okay, because in that case it's moving not at a very slow velocity, so the impact of the roughness is very extremely minimal. Okay, but for turbulent flow it is not. Okay, most especially for the fully rough turbulent flow. Okay, now in 1939 Colebrook and White advanced Nicolaus's work by applying sand roughness height to commercial pipes in the market to develop what is called the Colebrook-White equation, okay, which is the basis for what we are going to explain as Moddy diagram. Okay, so this is for commercial pipes. Okay, to find the roughness. Okay, the equivalent roughness, glass, plastic pipe, you can see because it's very smooth, plastic pipe, so 0. Okay, but others, copper or brass tubing, 0.0015. Others, you can see it increases. Riveted steel, very high. Okay, and also concrete, you see 0.3 to 3. Okay, very, very high, the relative roughness. So that means friction factor, the shear stress is going to be, the head loss is going to be very high in that case. Now Moddy presented a chart for commercial pipes using the Colebrook-White equation, and this is the commercial chart. Here is a chart in which you have 3 axes: the Reynolds number, this is the Reynolds number, and this is the relative roughness, okay, on this axis. And then on the other side, you have the resistance coefficient or the friction factor, okay, or the friction factor. The blue lines are the lines corresponding to the relative roughness for a given Reynolds number, okay. And for laminar flow, we all know that it is simply 64 over RE, okay. So this is for laminar flow, which you can simply find your Reynolds number and substitute. Okay, very straightforward. But for turbulent flow, that is when you need the Reynolds number and the relative roughness. You need these 2 parameters to get the value of the friction factor. How do we get the value of the friction factor using the laminar, using the Reynolds number and the relative roughness? You see, this is logarithmic scale. The Reynolds number scale is logarithmic. Okay, you can see 10 to the power of 3, 10 to the power of 4, 10 to the power of 5, 10 to the power of 6, 7, 8. In between, you have 2 to 8. Okay, so this is now like 1, 2, 3, 4, 2, then 3 is in between, 4, 5 is in between. Okay, like that. So this is logarithmic scale. Let's say you have Reynolds number of, let's say 10.5, 10.5, and the relative roughness is 0.02. This is the curve for 0.02, isn't it? Okay, so you follow the curve, okay, up to where you have Reynolds number of 10.5, which is here. Okay, you can see Reynolds number 10.5, and then you now project. So you go up using the Reynolds number 10.5, and then you follow the curve that has that relative roughness, which is 0.02, which is this curve. Okay, so where they meet, you now project it to get the friction factor. Okay, which we can say 0.026. Okay, which is this point. You see, the relative roughness are curves. What about if the relative roughness is 0.03? So here you are using an imaginary curve in between 0.002 and 0.004, okay, which is going to be somewhere in between, okay, somewhere in between, an imaginary curve in between, okay. Okay, so you like sketch it in between, okay, and then if you have Reynolds number of, let's say, 10 to the power of 4, you take it up, okay. Let's say you have Reynolds number 10 to the power of 4. Where it meets, you now project it to get the relative roughness, okay, which is more or less, in this case, is going to be 0.06, okay, 0.036, I mean, okay. So here, 0.036, okay, and here 0.026, okay. So this is how to work with the Moody's diagram. Above you have an equation also. This equation is for these black solid lines, okay. But in the examples we are going to look at, we'll be using this formula concept. We get the Reynolds number and the relative roughness, and then we project to get the friction factor. The relative roughness, we can get it from the pipe diameter and the pipe equivalent roughness coefficient, Ks, from a table. The Reynolds number from the pipe velocity diameter over the kinematic viscosity. Okay, we will take an example. The friction factor for all conditions is in an explicit way is given by this, okay, 0.25 over this. You see, this is the relative roughness, Ks over D. You can see that, okay, and this is the Reynolds number as well. And this you can use it, you know, to program, okay. When you can write codes, you can program it because you know, this one is using, you know, the Moody diagram, okay. If you are programming, if you don't want to be using that, you can simply put your RE here and your relative roughness here, and then find your friction factor, okay. But this is it is reported that this equation predicts friction factor that differ by less than 3%, okay, from those on the Moody diagram, for Reynolds number between 4 times 10 to the power of 3 to 10 to the power of 8, and the relative roughness 10 to the power of -5 and 2 times 10 to the power of -2. So this is the range of the applicability of this equation. Although it's you still get F to be slightly differing from the one obtained by Moody's diagram by just 3%. But still, for the sake of writing codes, writing computer programs, you know, calculations, this is also good as long as the conditions are satisfied, the Reynolds number and the relative roughness. Okay. Now, how do we solve flow in conduits? Okay, for laminar flow, it is simple, it's linear. But for turbulent flow, we have basically three cases. Case one is when the goal is to find the head loss. Okay, if we have the pipe length and diameter and the flow rate, this problem is straightforward because it can be solved using algebra. Okay, then we have a second case where we want to find the flow rate in this case. Okay, when we want to find the flow rate given the head loss or pressure drop, the pipe length and diameter, this problem requires an iterative approach or solver program. Okay, we need to use iterative approach. By iterative approach, it means we will assume the friction factor and get, let's say, the pipe diameter also, and get the Reynolds number. Okay, we assume the friction factor and then evaluate the Reynolds number and the relative roughness. Use these two to find the friction factor using the Moody's diagram, and then compare the friction factor with the assumed value. If they are equal, fine. If they are not, we now use this new friction factor, okay, to find the head loss and the Reynolds number again and the relative roughness, and find new F using the Moody's diagram. If this one and this one agree, then we stop. Otherwise, we now use the new value of the friction factor and repeat the process again. That is the iterative approach. We will demonstrate that using an example, okay? Then the third case is when the goal is to find pipe diameter, given the flow rate, length of pipe, and head loss. And this problem is also another iterative approach, okay? It's also another iterative approach in which we assume also the friction factor, evaluate the pipe diameter, and then find the Reynolds number, and then evaluate the friction factor using Moody's diagram, and compare the two, and then repeat the process again, okay? We'll look at some examples just now, okay? Swami and John and Streeter and Wiley, you know, these are several approaches that sometimes eliminate the need for an iterative approach. Okay, for case two, which is the iterative approach, can sometimes be avoided using an explicit equation developed by Swami and Jane. Okay, which is this: that the flow rate is giving. You can see even the equation. Okay, very very long. You have the head loss, frictional head loss, you have the relative roughness, and you have yeah, and that's it. Okay. So using this equation is equivalent to using the top of the Moddy diagram, which represents a scale for R, E, F to the power of half. For case 3, one can sometimes use an explicit equation developed by Swami and Jane, okay, and modified by Streeter and Wiley. That is to find the diameter when we have the flow rate and the head loss, okay? Now let's take this example. So in this example, here I want to find head loss in a pipe, which is case 1. Okay, so water at 20 degrees flows at a rate of 0.05 meter cube per second in 20 centimeter asphalted cast iron pipe. What is the head loss per kilometer of pipe? Simple. Okay, we have the flow rate, the length of the pipe, the diameter, and we assume that the flow is fully developed. Okay, and this is the property of water at 20 degrees, which is the kinematic viscosity. So the length of the pipe, because we said for per 1,000 per 1 kilometer, which is 1,000 meters. Okay, so here we calculate the mean velocity using the flow rate. Okay, this is the mean velocity. From the velocity, we can find the Reynolds number. Okay, and from the table, this table for asphalted cast iron, you can see the relative roughness is 0.12 in millimeter. Okay, so it's 0.12. Okay, so we can find the relative roughness. With these two, the Reynolds number and the relative roughness, we can go to the Moody's diagram and find F. Okay, we can look up 3.18 times 10 to the power of 5 and relative roughness 0.006. Okay, so we go to the Reynolds number, relative roughness 0.006, which is this one. You can see it, just this one. Okay, this curve, and then the Reynolds number 3 times Reynolds number 3.18 exponential 5. Okay, exponential 5. This exponential 5. So 3 will be somewhere here. Okay, 3.18. You can see, and then this is Ks over D 0.006. Okay, so where they meet. Okay, they meet somewhere here. Okay, can see, and then we now read the F here. Okay, so this is 0.015. Okay, so it will probably be 0.019. Okay, 6, 7, 8, so 0.019. Okay, which is the friction factor. Okay, and that's how we got this one. 0.019. Okay. And then we use the Darcy-Weisbach equation now to find the head loss, because the problem is asking us to find the head loss per kilometer. Okay, so we use the Darcy-Weisbach because it is turbulent flow, definitely. Okay, so HF, you can even see the Reynolds number 10 to the power of 3 times 10 to the power of 5. Okay, 3 times 10 to the power of 5, which if we write it in full, that is 318,000, not even 4,000, 318,000, which is, really turbulent flow. Okay, so here we get our F and substitute to get the head loss, 12.2 meters. Meaning, as the water is flowing, what is the meaning of this head loss? The piezometric head, drops by 12.2 meters. Okay, if this is the piezometric height here, when you put a piezometer, water rises to this point. After 1 kilometer, the piezometric head drops by amount equal to the head loss. Okay, equal to the head loss, which is 12.2 meters. Okay, this is the pressure head here, and this is the pressure piezometric head here. Okay, so it drops, it reduces. And why does it reduce? Because of the frictional head loss. as it is flowing, you see the mechanical energy is being converted to thermal energy, to waste thermal energy. That is a waste. We cannot use it. Okay, that's why the pressure of the fluid is decreasing. Okay, now this is another example in which we want to find the flow rate in a pipe for case 2. And in this case, we have water at 20 degrees, which flows from a tank through a 50 centimeter diameter steel pipe. Okay, and we want to determine the discharge of water. Okay, we want to determine the discharge. This is the elevation, 60. This is elevation here, 40. Okay, so water is draining from a tank through a steel pipe. We have the pipe diameter, and what else do we have? That's it. So we have the kinematic viscosity at 20 degrees. Okay, and the roughness coefficient, the equivalent roughness Ks for this type, which is steel. Okay, 0.046, which we can check. Steel pipe is steel. This is steel wrought iron steel, 0.046. Okay. So we can evaluate the relative roughness Ks over D, and there's the relative roughness, and here we want to find the discharge of water. Okay, and to find the discharge, we need to apply the energy equation for the two sections to evaluate the head loss. Okay, because as it is flowing, here the pressure is atmospheric. Okay, at 0.1 and 0.2, so they all cancel out. Okay, and the velocity at 0.1 is negligible compared to the velocity at 0.2, and we can find the velocity at 0.2 from, and is the elevation Z1 and Z2, which we know, and this is the head loss formula, which is the frictional head loss. Okay, so this is now the velocity, because we don't have Q, so we cannot find the velocity. That's why we have to use the energy equation. If we had Q, then we can simply find the velocity, but we don't have Q. And the question is asking us to find Q, okay? So that's why we cannot use V equal Q of A now, because Q is unknown. We have to go back and use the energy equation. So this is now the velocity in terms of friction factor. So here we can assume the friction factor. Here we assume it to be 0.02. And from the assumed value, we can evaluate the velocity, which is this, and then get the Reynolds number. And we already know the relative roughness. So go back to Moddy's diagram to get the friction factor, okay, based on this Reynolds number and this relative roughness. Okay, so from the Moddy's diagram, the friction factor is 0.012. You remember our assumed value of the friction factor is this one, 0.02. So this is different. So we use this again because these two, the assumed one is different from what we obtained from Moddy's diagram. We now use a new friction factor and repeat the process again. That's a second trial, okay? In the second trial, we use this F to find the velocity again, okay? And when we do that, the velocity now, instead of 8.86, is now 10.7. So we again calculate Reynolds number. Okay, the relative roughness remains the same because it's not a function of the velocity. Okay, so we go to Moddy's diagram again to determine the friction factor using this new Reynolds number and the relative roughness, which is the same as the previous one. The Reynolds number will change because the velocity has changed. The previous Reynolds number was 4.43 exponential 6. The current one is 5.35 exponential 6. Okay, so you can see the new friction factor is the same as the former one. So there is convergence. Okay, so the value of F is unchanged. Hence, we accept this as the correct value of the friction factor. Okay, 0.012. Okay, and then we use this now, since we now use this as the correct velocity to evaluate the discharge, okay, which is 10.7, and the discharge is simply VA. Okay, so this is the discharge through the pipe. So try as an exercise to see, to use this equation by Jane, okay, for the discharge. Okay, try to, yeah, but here you cannot use this because, yeah, because of the head loss. The head loss, yeah, because the head loss is a function of the friction factor. It's a function of the friction factor. All right. This is the second example. This is the friction Reynolds number, and this is the relative roughness. This is where they meet, and then we now have, where they meet, you have the friction factor, which is approximately 0.012. Okay. Now this is another example, the third one, in which we are to find the pipe diameter. Okay. So what size of asphalted cast iron pipe is required to carry water at 60 degrees Fahrenheit at a discharge of 3 cubic feet per second with a head loss of 4 feet per 1,000 feet of pipe? So here we are looking for what size of pipe. Size means diameter. Okay, we have the kinematic viscosity at this temperature and the roughness, the equivalent roughness for this asphalted cast iron pipe. Okay, and we have to calculate the pipe diameter, and the head loss is 4 feet per 1,000 length feet of pipe length. Okay, and here we have to develop an equation for use for the iteration using the Darcy-Weisbach equation, using the head loss formula. Okay, the head loss is given, but we don't have the diameter. Okay, we don't have the diameter, and we don't have the flow. The flow rate is provided. Okay, so here we substitute the velocity in form as Q over A. Okay, and so simplified. From here we can make the diameter the subject of the formula. In this case, we have HF, we have Q, we have L. The only thing we don't have is F, the friction factor, which we can assume and start the iteration. So iteration 1, initial guess. You can just guess any value, it doesn't matter, within the range, and then you keep on correcting. Okay, so here we start with 0.015. You can say, okay, I want to guess my F to be 0.02, and then you go ahead. Okay, so F 0.015, we substitute it here to get the diameter. Okay, once we get the diameter, we can get the velocity and the Reynolds number and the relative roughness, and use Moddy's diagram using this relative roughness and Reynolds number to find F. You can see this is the F from Moddy's diagram, and this is the assumed value of F, which are different, 0.015 and 0.0178. So we use this as the new value now, as the new F, and recalculate the diameter and repeat the process for the second iteration. Okay, and this is like in table, which you can use Excel. If you can program in Excel, it will be very pretty simple. Okay, for the first iteration, this is the assumed F, D, V. You calculate V, Reynolds number, you put the formula, relative roughness, new F. So this is the new value of F. You repeat the process again. You find D, V, R, E, this, and use the Moddy diagram. You see they are the same. 1 and 2 are the same. So F has converged. Okay. So if it has converged, then there is no need to continue. So you can simply use this as your final answer. So your diameter is now 1.00 feet, which is simply 1 feet. Okay. Which is simply 1 feet, okay, or 12 inch, because 1 feet is 12 inch. Okay, if you repeat for iteration 3 and 4, you can see the friction factor is remaining the same, it is not changing. Okay, so once you have two successive values that are agreeing very close, let's say within 10%, agreement, then you stop. Okay, hope it is clear. Now, for the remaining time we have, we'll quickly explain the minor head loss. Again, we talked about the major head loss, which is due to the frictional force, due to the shear force at the wall. But we still have the head loss is simply the sum of the frictional or major head loss and the minor head loss. Okay, this is the frictional head loss by the Darcy-Weisbach equation, and this is the general form of the minor head loss. Okay, which is the minor head loss due to the component, okay, components, valves, bends, and all that, okay. And this is a coefficient, minor loss coefficient, which depends on the component, okay. This is a minor loss coefficient, so it is simply proportional to the velocity head, okay. The loss coefficient is simply, the minor loss is simply proportional to the velocity head, okay. And it is proportional to the velocity head because the difference between the energy grade line and the hydraulic grade line is the velocity head, okay. And as you move on, the velocity head keeps on changing depending on both the head loss and the velocity within the pipe. Now, the combined head loss, when fluid flows through a component such as a partially open valve or a bend in a pipe, viscous effects can cause flowing fluid to lose mechanical energy. How does it lose the mechanical energy? By creating of separation zone, the work zone, okay? Work zone. We are going to show using some diagrams, okay? And the minor loss coefficient is simply, delta H over the velocity head, okay, which in terms of pressure, this is the change in the piezometric pressure over the kinetic pressure. This is the kinetic pressure, because we know that delta H is simply delta P Z over gamma, okay. So when we substitute this here, and gamma is what? Rho G, okay. So when we substitute delta H here as this, we will have delta P over, this is called kinetic pressure, okay? The kinetic pressure due to the kinetic energy, where delta H is the drop in piezometric head that is caused by a component, and delta PZ is the drop in piezometric pressure, and V is the mean velocity, okay? So here you have a component, okay, which can be a valve, okay? So generally the coefficient is the drop in piezometric head across component over the velocity head, which is simply based on the second one, the drop in due to the pressure drop due to component over the kinetic pressure. Now, head loss at pipe inlet and elbow. When you have, this is called flanged elbow, flanged, because it is smooth, okay? It has some radius here, okay? It's not sharp, okay? The streamlines are like moved closer to one another, and then there is possibility of attached flow separating here, okay? Creating separation zone, work zone. And in the work zone, you have huge energy loss as the flow is separated from the wall, okay? As it is separated, it is impacting a lot of drag force, okay? Drag force, a lot of energy loss is created in this separation zone, okay. This we explained when discussing about any separation, the attached flow and work region, when discussing the different types of flow, okay. So in this region you have separation zone, okay, which has a lot of energy loss, okay. The mechanical energy is lost there or converted to thermal energy. Okay. Now, what about when you have a very sharp entrance? Okay, you still have separation zone here created. Okay. Okay. The separation zone is sharper when you have a sharp entrance. Okay. Now, look at this. This is called the recirculating flow, which is the separation zone where you have the work region. See the coefficient of head loss 0.5 for sharp edge inlet. What about for well-rounded inlet? Okay, because for well-rounded inlet, the separation zone is smaller, is reduced. Okay, and the separation zone is what is responsible for the head loss. Okay, it's what is responsible for the minor loss at that joint. So when it is well rounded, the streamlines, the separation zone is minimized, and for that the coefficient of head loss is reduced. This is 0.5, this is 0.03, very small compared to the first one. Okay, and then here when you have, sudden expansion, okay, when you have sudden expansion, also there is attached flow that is separating. You have, separation zone, the work region here, which is created, which is responsible for the energy loss. Okay, because once the flow is separating, it exerts a lot of drag force, okay, which is part of the which is contributing to the energy loss. You have a work region. Okay, the same thing when you have contraction, okay, sudden contraction. Okay, when you have sudden contraction, you still have the separation zone here. Okay, but if you have a smooth, rounded, surface, it will be better. It will reduce the energy loss. Okay, if you have a smooth, rounded contraction surface, the energy loss will reduce. As you can see in this case, the energy loss is reduced because the minor loss coefficient is dropped significantly, by one order of magnitude. This is 0.5, this is 0.05, 0.03. Okay, and that is because of this. It is not a sharp edge inlet, it is well-rounded inlet. Similar to this one, if you can have it well-rounded, then it will be better. Okay, the energy loss will reduce. Is it clear? And you have a table which has the minor loss coefficients depending on the different cases. Okay, here you can see as R over D, that's the radius. This radius over the diameter increases. You see the loss coefficient, the entry loss coefficient drops. Okay, you can see from 0.5 to 0.03. Here as well, you can see a reduction in diameter. Okay, D2 over D1 as the uh, diameter reduces, okay, as they become close to the same diameter. When it is the same diameter, d2 over d1 we call 0. So, and this is the angle, okay, that is this angle. You can see theta. uh, the loss increases. Here it decreases because of the increase in the d2 over d, okay, meaning as it becomes very small and small, the energy loss is increasing. Okay, and this is for 90 degree smooth bend, and this is for meter bend. Okay, meter bend. Okay, you can see here 1.1. Here, depending on R over D, you can see as it is increasing, uh, as R over D is increasing, that is the sharper the bend. Okay, and this is KB. You can see this is 1.1, very high compared to even all the values here. Okay, and this is for threaded pipe fittings for valves. Okay, wide open, this is the valve loss coefficient. All right, let's take an example to see how to apply this. So the head loss, which is the sum of the frictional head loss and the minor head loss, is simply, given in summation form as pipes plus components, okay, which you can factorize the velocity head out and leave this. And this is the sum of the minor loss coefficient, okay? So this is the total head loss. But like we say, like I mentioned before, the minor loss coefficient is usually the minor head loss is usually very small compared to the major head loss, okay? So more often than not, we normally neglect them. So valid only if the diameter of the pipe in the entire system is the same. Okay, hence the velocity is constant. Okay, because here the velocity is constant. Otherwise, you'll have to separate it for each segment. And this is for all cases. Now let's take this example in which we have a pipe system with combined head loss. Okay, you have an oil here whose specific gravity is 0.9, and it flows from the upper reservoir, from the upper to lower reservoir, okay, at a flow rate of 0.028 meter cube per second in the 15 centimeter smooth pipe. What is the elevation of oil in the upper reservoir? We have the elevation in the lower reservoir, we want the elevation here. From here, you know you have to use the energy equation, okay? And you have R over D for both, R over D to be 2. This will guide us in getting the, minor head loss coefficient. And the minor head loss coefficient in table 10.5 for entrance, because you have for entrance here into the pipe, okay, which is 0.5. For bend, you have 2. R over D equal to, you have 0.9, 0.19, which is this. For entrance, this is for entrance, okay, 0.5. And then for bend, R over D equal to, so K, the minor loss coefficient is 0.19. Okay? But we have 2 of the bends, so okay, and you have outlet, the loss here also, which is the exit loss, which is this one now. Entrance, expansion, yeah, exit loss, which is this one, okay, which is this. So what did we use here? We used 1, okay, KE equals 1 expansion, okay, you can see KE, the exit, okay, equals 1, okay, for 180 degrees, meaning straight, okay, for 180 degrees, okay, KE equals. So now we apply the energy equation. We don't have pump, we don't have turbine, okay, and then the pressure, it cancels out because it's atmospheric, okay, it is atmospheric, and then again we have the velocity to be the same, okay, so we have Z1 equals Z2 plus the head loss, and the head loss is sum of the pipe head loss and the component head loss, okay. The component head loss, we have 2 bends, that's why we have 2 times KB here, okay. We have the entrance head loss, we have the exit head loss, okay. So we factorize this and substitute all the coefficients. We can find the velocity Q over A, simple, and the Reynolds number. And then here, that's the flow is turbulent, okay? So here we use the Swami-Jain equation to find the friction factor rather than the Moddy's diagram. Try to check with the Moddy's diagram, okay? So this is F. Once we find F, we can come here and substitute it, to get Z1, simple. Okay, so Z1 now is 136. Okay, Z1 is 136. And if you sum everything, the pipe head loss is 47.2. The component head loss altogether is 1.88. So the pipe losses is far, far greater than the minor losses. That is why we normally ignore it. Okay, 47 and 2. Okay, very small. Okay, so in the next class, we will look at the design of pumps and system curve, and then that is it. Okay, that will be all for the chapter. Now, it is about the 5% for assessment. So I want to maybe instead of having, asking you to sit and take a homework, a question from the homework, do we just add it to the homework, maybe increase the grading for the homework, the assessment for the homework? Let me check how much is it assigned for the homework. As per the syllabus, Yeah, as per the syllabus, homework is 10%, and we have quizzes 5%, and attendance and participation 5%, and assessment 5%. So quizzes is having 5%. Okay. So maybe do we just add it to the quizzes so that we make it now the quizzes to be 10% instead of 5%? Yes, can you all hear me? No, homework is already 10%, and the quizzes we have it only to be 5%. I was thinking before maybe the homework was 5%. Okay, but homework is already 10%. So I will suggest we add it to the quizzes to make it quizzes not good. We can give one more quiz. Okay, next week. Let's give one more quiz next week. Okay. Let's say what one more quiz, Dory. In which chapter now? I have energy equation. Did I give you quiz? Okay, let's say on the energy equation, chapter 7. Okay, so let's schedule a quiz next week, and then take a quiz on the energy equation, which is chapter 7. And then this 5% we now make quiz instead of 5% to 10% now. Okay, instead of asking you to come and take some questions from the homework. Okay. Because now we're almost through chapter 10. We have chapter 11, 15, which is the open channel flow. Okay, and then I am done grading all your homework. Sorry, all your quizzes. So I will start by next week. I will have to finish grading all your homeworks as well. Okay, by next week I should be through grading all your homeworks. Okay. All right.